Assalamu alaikum class. In this video we are going to start chapter number 3, vector differentiation. So as far in chapter number 1 we discussed about the vectors, and in chapter number 2 we discussed about some algebraic operations operated on vectors, and now we are going to discuss that how differentiation is applied on vectors, as we know that what is meant by derivative and how we can find out the derivative of some functions as in calculus or math 1 or 2. But now we are going to apply the rules on vectors, that how we can differentiate different vectors, because we have discussed earlier that vector field itself is a function. So vector differentiation, in vector differentiation the first topic we are going to discuss about is ordinary derivatives of vectors. So let r of u be a vector depending on a single scalar variable u. Here make sure that u is a scalar variable, not a constant term, and delta u be an increment in u. Then as we know that by definition derivative is defined as f, limit h approaches to 0 f of x plus h minus f of x over h. Similarly we are going to define the derivative of vector on the same basis. So let's suppose this is my vector r of u, and I am adding some vector delta r, because we have to increase the vector by a smaller amount, or we have to increase the function by a smaller amount. So we are adding a vector in the previous vector r. So r plus delta r is going to be the resultant, that is r of u plus delta u. So clearly r u plus delta r will be equal to r of u plus delta u, that is r of u plus delta u minus r of u will be equal to delta r. So here is the value of delta r over delta u. Now by definition it will be equal to the derivative by taking the limit h approaches to 0, or in this case it will be delta u approaches to 0. So here we have defined the derivative of r of u with respect to u as limit delta u approaches to 0, r of u plus delta u minus r of u over delta u if the limit exists. So this is the same as we discussed for functions in calculus, but this is by definition obviously, but we perform differentiation with the help of rules. So similarly we will perform the differentiation of the vectors with the help of rules as well, but we should know what is the derivative by definition. So here the representation for the derivative dr by du, obviously this one is a vector quantity, so we can again differentiate it with respect to u, that is a double derivative or the second order derivative. Similarly we define the higher order derivatives as well. Now before defining the vectors properly, or before defining the rules of differentiation, we define the space curves, because we apply the derivatives on functions, and functions define the curves. So if we are talking about the 2D function or the one single variable like y is equal to f of x, we know that it is going to define, or it is going to draw the when we draw the graph of such functions we are going to have a curve which is going to lie in the plane. But now we are going to discuss about the space curve. So plane curve must lie in a single plane, that is it could be xy plane, yz plane, or even xz plane. So the plane curves must lie in a single plane, that is a two-dimensional figures, whereas a space curve always pass through a region which is basically a three-dimensional space. So space curves means we are talking about the three dimensions, and plane curves means we are talking about the two dimensions. So consider a vector r of u depending on a scalar variable u. If r of u is a position vector joining the origin O of a coordinate system and any point P, as we have discussed earlier that we can define the position vector with respect to origin by joining the point from origin. So P of x, y, z, and clearly the components of the vector r will be x, y, and z. So here we have defined x, y, and z. Clearly the specification of vector function r of u defines x, y, z as a function of u. Here we can see that x, y, and z are functions of u, but these are the scalar functions, not the vector functions. R is the vector quantity. Now when u changes, r of u represents a different point in 3D space. Therefore the terminal point of r describes a space curve with parametric equations x is equal to x of u, y of u, and z of u. So why we are saying it to be the parametric equations, because we know that in parametric equations we define all the functions or all the equations with the help of one single parameter. And here you can see that we are not saying that x, y, and z are different functions, or the functions depending on the different variables. All the functions are depending on the one single variable u, and if I change the value of u, the point is going to change completely, because by changing the value of u, x, y, and z are going to have the different value. So for example, if x is equal to 2u y is equal to u and z is equal to 3u. So when I'm going to take u is equal to 1, I am going to have a 0.213. when I take u is equal to 2, I will have the 0.4, 2 and 3. So you can see that by changing only one variable u, we are going to have a totally different point. That's why these are named as the parametric equations. So here is the graph of some space curve. It is an arbitrary space curve. This is lying in a space not in the plane right now. So let r of u is equal to x of u, I cap, y of u, j cap, and z of u, k cap. As we have discussed, these are the parametric equations or the parametric functions. Here x, y, and z are differentiable functions of scalar u. We have to prove that the derivative is basically dx by du, dy by du plus dz by du. That is, we are taking the derivative of each component separately. This is nothing difficult in it, that if we have to take the derivative of a vector, we have to take the derivative of each component separately. That's it. So here is the proof as well. We know that dr by du is equal to, by definition, limit delta u approaches to 0, r of u plus delta u minus r of u over delta u. So clearly u plus delta u is basically, we are changing u, so the components of this vector are going to be x of u plus delta u plus y of u plus delta u and z of u plus delta u, and this r is going to have the vectors x, y and z, or the x of u, y of u and z of u. So now separating the I, j and k components, we get this form, and this is going to be dx by du, because x, y and z are differentiable functions. So by definition, this term will be equal to dx by du, dy by du and dz by du. So what we have to prove in this case? If u is the time t, then obviously dr by du will be represented as dr by dt, and it will represent the velocity. And by taking the derivative of velocity, we talk about the acceleration, and we know that dv by dt is basically the double derivative of the position vector. So here we can see that in question number 2, we are given with the function r sine t I cap plus cos t j cap plus t k cap, and here you can see that the variable u is replaced with t, nothing else. So we have to find out dr by dt, that is the first derivative of the vector r. So we are just taking the derivative of the components separately. So derivative of sine plus I cap plus derivative of cos j cap plus derivative of t k cap. So sine t derivative is basically cos t. The derivative of cos will be equal to minus sine, and derivative of t with respect to t will be equal to 1. So here is my derivative of the given vector. Next we have to find out the double derivative d square r by dt square. So here is the double derivative. So double derivative means I'm going to take the derivative of the first derivative. So here is my first derivative. Now derivative of cos will be equal to minus sine, and derivative of sine will be equal to cos, and derivative of 1 will be equal to 0. So minus sine t I cap minus cos t j cap is the double derivative. Then we have magnitude of dr by dt. So how we can find out the magnitude of dr by dt? Square root of x component square plus y component square plus z component square, and we know that cos square plus sine square is always equal to 1. So 1 plus 1 will be equal to 2. That is, the magnitude is square root of 2. And the fourth one is the magnitude of d square r by dt square. So here is my d square r by dt square, and for its magnitude we will take square root sine square t plus cos square t, which is equal to 1. You have to attempt question number 3 on your own, and we are going to discuss question number 4. A particle moves along the curve x is equal to 2t square, y is equal to t square minus 4t, and z is equal to 3t minus 5 where t is the time. So these x, y and z are basically defining the x, y and z components of the position vector r, and we have to find out the components of the velocity and acceleration at time t is equal to 1 in the direction of the given vector. So you can see that here is the x, y and z components that are defined in the question. X is equal to 2t square, y is equal to t square minus 4t, and z is equal to 3t minus 5. And for velocity, we have to take the derivative of the position vector r. So here you can see dr by dt is the derivative of the function. So 4t I cap plus 2t minus 4j cap, and the derivative of this function will be equal to 3. So 3k cap. So here is my velocity vector, and we have to find out the velocity at time t is equal to 1, so we will put t is equal to 1, but it will so putting t is equal to 1 in this function, we will get 4 I cap minus 2 j cap plus 3 k cap. Now we have to find out the component of the velocity in the direction of the given vector. So we know that to find out the direction only, or to deal with the direction only, we will find out the unit vector. So for this we will find out the magnitude first. So the magnitude of the given vector, which is basically I cap minus 3 j cap plus 2 k cap, its magnitude is the square root of 14, and by dividing the vector with its magnitude we get the position vector. Now for the component of the velocity in the direction of this vector, we will take the dot product of velocity with the unit vector, this one. So here we have defined the dot product over here, so we get the answer 8 square root of 14 over 7. Next we have to find out the component of acceleration in the direction of given vector as well, and for acceleration we have to take the derivative of velocity. So here is my velocity vector, and by taking its derivative I will find out the acceleration vector. So its derivative will be equal to 4 plus 2 j cap plus 0 k cap. And now for the component of acceleration in the direction of given vector, we will find out the dot product of the vector with the unit vector. So here we get the answer minus square root of 14 by 7. Next we are going to talk about the continuity and differentiability. As we know that we are talking about the differentiation, so whenever we talk about the derivatives, we can talk about the continuity as well. So we are going to discuss about the relation between the continuity and differentiability for the vector functions. Now we know that in calculus a function f is said to be continuous at a point C if the functional value and the limiting value both have the same expressions, that is f of x is equal to limit x approaches to C f of x. So we are defining that a scalar function phi of u is said to be continuous at u if limit delta u approaches to 0, phi of u plus delta u is equal to phi of u, that is the limiting value is equal to the functional value. So same holds for the vector functions as well. So here is a definition for the vector function, that the limiting value must be equal to the functional value. And clearly when we talk about the vector function, it is basically an addition of or the resultant of three scalar functions, r of u along I cap along x-axis, r of 2 r2 of u with j cap, and r3 of u with k cap. So if all these three functions are continuous, then obviously their resultant will also be a continuous function. Now we know another form of continuity, that is epsilon delta form, that phi of u is said to be continuous at u if for every epsilon positive there exists a delta positive such that phi of u plus delta u minus phi of u is mod is less than epsilon whenever delta u is less than lambda. Here epsilon and lambda are very small numbers, so basically this expression is letting us know that phi of u plus delta u and phi of u are very close to each other. That's where their difference is really equal to 0. So this is saying that the two terms are very close to each other whenever delta u is very close to 0. That is we talk about the this is what we talk about the continuity, that the limiting value must be equal to the functional value. As we say that delta u approaches to 0, so this is saying that delta u is approaches to 0, and this expression will be equal to this is saying that their difference is really equal to 0, that is they are very close to each other or nearly equal to each other. So same holds for the vector functions, just we are having a notation of vectors over here. The definition is the same.